Welcome to the shores of the statistical ocean and the sea of statistics is all that is data, ever was data, or ever will be data. You are here to explore that data. This series is to act as an introduction to the concepts of statistics and her brethren. You will delve into the art and science behind understanding our universe through testing and observation, proportions and randomness, probability and inference, and finally, most importantly, you will be able to understand and explain your findings to the rest of the world. Let's go in. You'll soon realize how statistics is everywhere and how pertinent it is to everyday life, even as I walk through the halls of Freedom High School. Here we are, Ms. Drasley's AP Statistics classroom. What a wonderful start. Stop, look, and listen. Relax, and do not be alarmed. We are in a magnificent realm of the statistical universe. You are in good hands as well. Keep an open mind and observe with your senses and imagination. Our statistics journey begins right now.
Now let's begin exploring data. Okay, today we're going to be learning about two different types of data points. Qualitative data points and quantitative data points. The difference is that this has no units. Okay, so we're going to be collecting eye color. Evan, what is your eye color?
Green.
Ali?
Blue.
Jessica?
Hazel.
Vandana?
Brown.
Nabil?
Brown.
Simran?
Brown.
Carolyn?
Brown.
Okay, and now we're going to collect some more quantitative data points. So, what is your height, Evan, in inches?
75.
Jeez.
Ali?
55.
Holy crap.
Jessica?
48.
Sweet.
Vandana?
51.
I highly doubt that. Nabil?
84.
Good job.
Simran?
65.
Cool.
Carolyn?
91.
Wow.
Nice.
Mount Everest.
Okay, now we're going to graph these data points.
Now let's begin displaying statistics. Now this is the bar chart. You'll notice that each of the boxes are separated by a space. On the x-axis are the categories. On the y-axis are the counts. Now here's another way of displaying qualitative data. A pie chart, or not a pie chart, because it violates the area principle. We'll learn about that later with Ms. Drazy. Another way of displaying qualitative data is a frequency table. Here are the categories and here are the counts.
Understand that, boys and girls? Uh-huh.
Now we'll look at ways to display quantitative data. Here's an histogram of the heights we took early today. As you can see, the histogram is unimodal, meaning there's only one high point here. However, it's extremely skewed to the right, meaning that the mean is probably very higher than the median.
So this value going from 51 to 84, this box, shows the middle 50% of the data. Now, there's values called outliers, which lie outside what we call the norm of the data. We can find outliers by doing this equation, 1.5 IQR. IQR is interquartile range.
Statistics!
So, 1.5 IQR, that would be 1.5 or 33, 49.5. So now we have 49.5, and anything above our third quartile, 84 plus 49.5, would be considered an outlier. So let's say it was 250. Since that is 49.5 above 84, then it would be considered an outlier. Also, anything below 49.5 below quartile 1, which is 51, would also be considered an outlier.
So just like we just saw on the video, this is a normal model. Now the mean of our heights was 67, or the average value. Now 83.8 and 50.2 and all these other values are standard deviation. The standard deviation is the average distance that each point is from the mean. Now the notation for the mean or average value is x bar, and the notation for standard deviation is little sigma. Now, this is another picture of a normal model. You'll notice that instead of 67, we have 0. This is a standardized normal distribution. Now, it's evenly distributed, unimodal, and symmetric. From one standard deviation away from the mean is 68% of the data. 2 standard deviations is 95% of the data. And 99.7% of the data is from -3 to 3. Now, disease score. In order to calculate the z-score, or the standardized value of one of our points, you need a star equation. C equals x, the value that we're looking at, minus x bar, our mean, over the standard deviation. Now it is 56 minus 67 over 16.8. And that value is -0.65. So if we go back, that means that 56 is about -0.65 standard deviations away from the mean.
Okay, class, today we're going to learn about linear regression. Yay! See, he's excited, okay? So now, let us pretend we have a graph like this, where this right here is time, and this will be bacteria. And we want to graph the rate of bacteria growth over time. If we had a truly linear graph, it would look like this.
Now, that was a strong positive association because it has a slope that's very close to 1. Now, a strong association would be close to 1, -1, or 0. In this case, it's 1, and making it positive. Now, you can see that it's very close to up 1 over 1, up 1 over 1.